Welcome to the deep dive. Today, we're really focusing on that critical moment for large language models.
That moment after pre-training.
Exactly. The
Yeah.
post-training alignment phase. This is where you take that, huge general model.
And turn it into something useful, something that follows instructions, something ready for production.
Right. And that whole alignment process, it covers fine-tuning, reinforcement learning.
Right.
It's complex.
It's arguably the biggest bottleneck right now, especially if you're working in the JAX ecosystem.
Yeah, historically, JAX users have had fewer off-the-shelf tools for this.
Yeah.
A lot of building from scratch.
Or wrestling with abstractions that maybe didn't quite fit. So today we're diving into two libraries meant to fix that.
Good.
There's the foundation, Flax NNX, which is a sort of API rethink.
And then built on top of that?
Tunix, which stands for Tune In JAX.
Ah, clever. Tune in JAX. So the focus is alignment.
Yep. High-performance LLM alignment. Tools for SFT, RL, distillation, the works, but designed for control.
Control being the key word, you think?
Absolutely. That's the promise. But to really get Tunix, we need to start with its base, with Flax NNX.
Makes sense. Lay the foundation first. So JAX is known for pure functions, immutable PyTrees. Great for speed on TPUs.
Definitely. That purity is its power.
But maybe not always the most intuitive if you come from, say, PyTorch or Keras. That immutable state can be tricky.
It can feel a bit different, yeah. NNX is really about improving the developer experience there. It brings in first-class Python reference semantics.
Okay, reference semantics. How does it achieve that within JAX's constraints?
The key shift is modeling networks not as standard JAX PyTrees, but as something called pygraphs.
Pygraphs instead of PyTrees. Why is that specific change so important for the developer? What does it unlock?
Well, pygraphs allow for reference sharing and, crucially, mutable state within the model structure itself.
Mutable state. In JAX, that sounds different.
It is for traditional JAX. But think about object-oriented programming. You create an object like a layer, you modify its attributes, maybe its weights, you call methods on it directly.
Right, standard Python class.
And NNX aims to give you that familiar feeling. It tries to bridge that gap between standard OOP and JAX's functional core. Make PyTorch users feel more at home.
Okay, that sounds easy to write, maybe more intuitive for many folks. But JAX's performance relies on explicit tracking. You mentioned NNX is highly explicit. What does that mean day to day, like for parameters or random numbers?
It means nothing's hidden under the hood, really. An NNX module holds its state-like trainable weights directly. It uses explicit types like nx.param.
Okay.
And it's eager. You call the constructor init, and the parameters are created right then and there.
No delayed initialization or shape inference.
Nope. You need to provide shape info upfront. And critically, you, the user, are responsible for handling the PRNG state, the random number generator keys. You have to thread those through your functions explicitly.
That sounds like potentially more boilerplate compared to frameworks that manage RNG state automatically. Is that a drawback?
It's a trade-off, definitely. A bit more code up front, but the huge win, especially for complex models, is debuggability.
How so?
Because everything is explicit. You know exactly where state is coming from and going to. No hidden side effects, no implicit state being passed around in a complex compiled graph, which can be a nightmare to debug.
Right. You can trace things more easily.
Exactly. Plus, you can just call methods directly on the module instance. No separate apply method, like in older Flax or Haiku, makes inspecting things much more straightforward.
Okay, so let me try to synthesize that.
Yeah.
NNX gives us a more familiar, object-oriented way to define models. Closer to PyTorch, maybe.
Yeah, that's the goal.
With easier debugging, because everything is explicit, but still leverages JAX for performance.
You got it. That's the essence.
All right. With that foundation laid, let's build on it. Enter Tunix for the actual post-training work.
Exactly. Tunix takes that NNX base and provides the tools for SFT, RL, and distillation. High-performance JAX native.
And you mentioned its design philosophy earlier, the white box approach. Tell me more about that.
Yeah, white box. It's really about minimizing abstraction debt. Some frameworks, they build layer upon layer of abstraction.
Which can be convenient sometimes, but also opaque.
Right. It can get in the way if you need to customize things deeply or if you're doing research. Tunix tries to give you the core components, the building blocks, but leaves you in full control of the actual training loop and the post-training logic.
The sources mentioned some research emphasizing why that control is so important, particularly for iterating on data.
Yeah, that was interesting work from Brandeis. Their point was, in research, you're constantly tweaking things. Maybe looking at specific data samples, trying different gradient accumulation strategies, modifying how you collect data. If your framework has too many rigid layers, making those kinds of changes becomes incredibly difficult, maybe even impossible. Tunix is designed to avoid that pain, making it easier for developers to experiment quickly.
Okay, rapid iteration is key. But these are huge models. Performance is non-negotiable. How does Tunix handle scale, training on TPUs, multi-device setups?
It's built for it from the ground up. Being JAX native means it plays very well with TPUs. It's often used alongside systems like MaxText for really large-scale training.
And sharding strategies, data parallelism, tensor parallelism.
All the standard ones are supported natively. Data parallel, DP, fully sharded data parallel, FSDP, tensor parallel, TP. Because it's built on JAX and leverages that ecosystem, scalability isn't an add-on. It's part of the core architecture.
Got it. So let's walk through the actual algorithms Tunix offers, starting maybe with the most common, supervised fine-tuning, SFT.
Right. For SFT, Tunix provides the PEFT trainer. It's pretty flexible, model agnostic. It can do full fine-tuning, updating all the weights.
But often we don't want to update everything. Yeah, especially with massive models.
Exactly. So the real power often comes from its support for parameter-efficient fine-tuning methods. PEFT.
Like LoRa.
LoRa, yes, and QRA, which uses quantization for even more efficiency. Tunix integrates with another library called Quix to handle the QRA specifics.
So you can get significant alignment improvements without the massive compute cost of full fine-tuning.
That's the idea. Makes fine-tuning much more accessible.
Okay, moving up in complexity. Beyond just following instructions, we want models to align with human preferences. That brings us to preference tuning, specifically direct preference optimization, or DPO.
DPO. Yeah, this has been a really impactful technique. It simplifies things a lot.
How so? What does the DPO trainer in Tunix do differently?
Well, traditional RLHF reinforcement learning from human feedback usually involves training a separate reward model first. You collect preference data, which response is better, A or B, train a model to predict that preference.
And then use that reward model in an RL loop. Which sounds like multiple complex steps.
It is. Training that reward model can be unstable, data-hungry, tricky to get right. DPO, implemented in the DPO trainer, cleverly bypasses that entire step.
Bypasses the reward model.
It uses the preference data pairs of preferred and rejected responses directly to fine-tune the language model itself. There's some neat math behind it, but operationally, you just need that preference data set.
Wow. So you skip the whole reward modeling phase. That must save a lot of time and resources.
Huge operational win, yeah. Less complexity, fewer models to manage, potentially less sensitivity to reward model calibration issues. It's a much more direct path from preferences to aligned model.
Okay, very cool. Now for the really complex stuff. Reinforcement learning for alignment, especially for sequences and agentic behavior. Tunix offers PPO.
It does. The PPO learner implements proximal policy optimization. That's still kind of the gold standard, the workhorse actor-critic method. If you need complex, multi-step reasoning or tool use, PPO is often the go-to.
Actor-critic meaning it learns both a policy, the actor, and a value function, the critic.
Correct. But remember that white box philosophy, Tunix also provides options that are perhaps leaner, maybe more experimental.
And that's where these group-based methods come in, like GRPO.
Exactly. GRPO stands for Group Relative Policy Optimization. The GRPO learner implements this. And the really interesting thing, it's critic-free.
No critic. How does it learn without estimating future rewards?
Instead of learning an absolute value function, it looks at a group of responses generated for the same prompt within a batch. It then normalizes the rewards relative to the average reward within that group.
Okay, so it's comparing responses against each other directly.
Sort of, yeah. This relative comparison guides the policy update. It avoids the need to train that often noisy, high-variance critic model.
Which likely means it's computationally lighter, maybe more stable.
Potentially, yes. Lighter, maybe easier to tune in some cases. And then there's a variant called GSPO token.
Group Sequence Policy Optimization. How's that different from GRPO?
GSPO token builds on GRPO, but offers more flexibility in how the advantage signal is calculated at the token level. This can be particularly helpful for stability in multi-turn RL scenarios.
Multi-turn, like longer conversations or tasks.
Right, where the sequences get long and dependencies build up. GSPO token provides finer control over the credit assignment, which can improve training dynamics for those more complex, longer horizon tasks.
Makes sense. So we've covered alignment, but deployment often demands efficiency. That brings us to knowledge distillation.
Yep, the distillation trainer. Essential for model compression. You have your huge, powerful teacher model.
The one that cost a fortune to train.
Exactly. And you want to transfer its knowledge to a much smaller, faster student model that you can actually deploy cost effectively.
So Tunix helps manage that transfer. What kinds of distillation does it support? Just matching output probabilities.
It supports the classic logic-based distillation, where the student tries to mimic the teacher's output probabilities, the soft targets.
Okay.
But it also gets into more advanced methods, things like attention transfer or feature pooling and projection
How
strategies.
does those involve?
They go deeper. Instead of just matching the final output, they try to make the student model replicate the internal representations or activation patterns of the teacher model at intermediate layers.
Matching the thinking process, not just the answer.
Kind of, yeah. And the cool thing is, these methods can sometimes work even if the teacher and student models have different architectures.
Oh, interesting. So you could distill from, say, a big transformer to a smaller RNN or something completely different.
Potentially, yes. It gives you more flexibility in choosing your efficient student architecture.
Very useful. Okay, one last area. Agentic AI. Models that don't just talk, but do things. Interact with tools, environments.
Right, the really cutting-edge stuff. Tunix is being used here, too. The sources mentioned Precur AI as an example.
What are they doing?
They're using the whole Tunix stack, SFT, RL distillation to create what they call specialized agent kernels.
Agent kernels.
Yeah, think of them as LLMs fine-tuned for specific, long-running, often repetitive tasks. Maybe tasks that need to run reliably in the background. Using Tunix gives them a unified JAX framework for all the necessary post-training steps.
That unified stack must simplify things a lot.
Definitely. And the Tunix roadmap reflects this focus, too, with plans for features specifically for agents like asynchronous rollouts, better multi-step support, tool usage capabilities.
Sounds comprehensive. But does it actually work? Is there quantitative proof these methods implemented in Tunix deliver results?
There is. They provided a specific example, fine-tuning the Gemma 2 2BIT model using their GRPO implementation.
Okay, Gemma 2B, a decent-sized open model. What was the task?
The GSM-8K math reasoning benchmark, which is notoriously difficult, requires step-by-step logical thinking.
And the result?
They reported roughly a 12% relative improvement in pass at one answer accuracy compared to the base instruction-tuned model.
Wow, 12% relative lift just from the GRPO post-training on math reasoning. That's actually quite significant.
It is, and they checked it across multiple metrics, not just the final answer, but also partial accuracy, just getting close, and format accuracy following the reasoning steps. So it suggests a genuine improvement in the model's reasoning capability.
That's solid evidence. So for people working in JAX, or maybe wanting to leverage Google Cloud TPUs more effectively for alignment,
Tunix seems like a really compelling option to look at. It bridges that gap between JAX performance and maybe more familiar PyTorch-style development for model definition via NNX.
and it's available now. People could try it.
Yep, it's on PyPI. Pip install Google Tunix. The repository apparently has examples to get started, like using PFT with QLaRA or training with GRPO.
Excellent. It sounds like it offers that powerful mix, performance control, and a comprehensive set of alignment tools.
That seems to be the goal, giving researchers and developers the tools they need without boxing them in.
Right. Which brings us back to that white box idea and maybe a final thought for you, our listener. This whole conversation highlights the power of having direct control over the training loop, fighting back against too much abstraction. So the question is, if you had that level of granular control, that white box access, what specific research idea, maybe something focused on data quality or a unique iteration strategy, would you try first? What's something you couldn't easily do before because the framework got in the way?
Yeah, what becomes possible when you can truly tinker with the internals? That's where the next breakthroughs might come from.